negative of getting older is it's harder to sleep in when you want to. You just wake up no matter what. It's just not. I would prefer not to have to do that. All right, so from chapter 13, last semester, we talked about the total differential. So this is just a little reminder. The total differential of z equals f of xy, we said we wrote it as dz, is the partial of f with respect to x dx plus the partial of f with respect to y dy. And the context that we had then was we were talking about an approximation of we're using the change in the height of the tangent plane to approximate the change in a function. If f of xy equals a constant, well, the derivative of the constant is 0, in that case, our total differential is 0. And this is a first order differential equation, where these are our coefficient functions and these are our differentials. So we're going to say m of xy dx plus n of xy dy is an exact differential if in some region of the plane it corresponds to the total differential of some function. So this is going to be an exact differential if it's the total differential of some function. Well, that means that m is the partial of that function with respect to x, and n is the partial of that function with respect to y. We have seen this situation before, where this was the partial of some function with respect to x, and this was the partial of some function with respect to y. We saw that when we were talking about conservative fields. So I'm just going to say f of xy is our function in the region. And we call the differential equation, if this thing equals 0, we call that an exact equation. if our left-hand side is an exact differential. So if we have an exact equation, this is the partial of some function with respect to x. This is the partial of some function with respect to y. How do we tell if it's exact? I'm going to say we can tell this if the partial of m with respect to y equals the partial of n with respect to x. So this differential equation is an exact equation. This expression is an exact differential if the partial of m with respect to y is the partial of n with respect to x. Just like the test for conservative fields in the plane. This is exactly the test for conservative fields in the plane. This is how we told if this was this m xy n xy was a conservative field. And this comes exactly from, for the exact same reason. If this is the partial of some function with respect to x, and we take the derivative with respect to y. If this is the partial of some function with respect to y, and we take the derivative with respect to x, those are the mixed partials. The mixed partials have to be equivalent. So we solve this differential equation exactly the same way we found a potential function for a conservative field. We integrate our component functions. We integrate m with respect to x. We integrate n with respect to y and adjust the constants so that we get the same thing. So let's look at an example. We want to solve 2x plus y dx minus x plus 6y dy equals 0. Well, I take if this is m and this is n, partial of m with respect to y is 1. Partial of n with respect, with respect to, is that what I want to do? What did I do here? Partial of m with respect to y, that's right, is 1, and partial of n with respect to x is 6, negative 6, sorry. Today, yeah, that should be -1, sorry. So this is not exact. So we don't really know how to solve this. If we rewrote this, dy dx, some function of x, we would see that's neither separable nor linear. So if we try to make it a separable equation, it wouldn't work. If we tried to write it as a first order linear equation, it wouldn't work. So right now we don't know how to solve this. So we can't solve this one. Not exact. I'm not going to say no solution. I'm going to say we don't know how to solve this one yet. All right, let's look at another one. Still solving. Sine y minus y sine x dx plus cosine x plus x cosine y minus y dy equals 0. Now, in this section, we know that these are exact. If we weren't not exact, but it's in the form of an exact equation. So we were going to do our test. If we're not sure, we could rewrite this dy dx and see if it's linear, see if it's separable, see if it's a first order linear, something that we already know how to solve. If not, then we can test to see if it's exact. So if this is m and this is n, the partial of m with respect to y is cosine y minus sine x. Partial of n with respect to x is minus sine x plus cosine y. So it is exact. So we want to find our function. So I'm going to integrate this with respect to x and integrate this with respect to y. So integral of sine y minus y sine x dx. And remember, we're integrating with respect to x here. So this is going to be x sine y minus y cosine x plus possibly some function of y, because we're integrating with respect to x. And a function of y is going to be constant with respect to x.
Plus y cosine x for my
Uh,
cosine switches.
yes.
Okay.
So integrate n with respect to y, and we get the integral of cosine x plus x cosine y minus y dy. And when we integrate that, I get y cosine x plus x sine y minus y squared over 2 plus possibly some function of x. And we compare these two. So these are the same. So our g of y is minus y squared over 2. And we say that our solution, f of xy, equals x sine y plus y cosine x minus y squared over 2 plus a scalar constant, and that equals 0. That is our solution. And we get an exact equation when that function equals 0. Did I write?
Yeah, he thought your sine
This should be x sine, yeah, that's a sine y.
There's sine y.
And then this is a cosine x, y cosine x, is that right? I switched my x's and y's there. And if we wanted to look at solution curves here, see what this solution curve looks like in the plane, we can go to our, our plotter, just so we can look at that. All right, here's our function. Y cosine x plus x cosine y sine y. Minus y squared over 2. There are our solution curves. That's a pretty crazy. That's a pretty crazy looking function.
It looks like a frog. You know, like the little part, like the tentacles.
It literally just looks like a generic, like, topographical map. Like, there's a little hill there, and it's like some kind of range.
Oh, maybe it's like a volcano and the other two are islands.
Yeah. So that's an interesting looking function there.
You're gonna have to graph a couple of those on the class.
By hand. Yeah, I'm not going to make us do a lot of graphing by hand in this class. Let's look at an initial value problem, and then we'll stop for today. E to the x plus y dx plus 2 plus x plus y e to the y dy equals 0. And y of 0 equals 1. Well, if that's m and that's n, see if I can write my derivatives correctly this time. Partial of m with respect to y is 1. Partial, oh, this is easy for me. Partial of n with respect to x is 1. Got that? So there, it is exact. This is an exact equation. So I'm going to integrate m. I'm just writing out what we're doing with respect to x. So I'm going to integrate e to the x plus y dx. And we get an easy integral. E to the x plus xy, is that right? Plus possibly some function of x. We integrate n with respect to y. So I'm going to integrate 2 plus x plus y e to the y.
You added an extra x.
Add in an x. Is this just a 2? Yes. 2, Oh, and I need a dy. 2y. I was looking at my answer already. 2y plus x, y, plus, this is an integration by parts. This one comes up frequently enough, we might memorize it by the end here. This is y e to the y minus y. Sorry, minus e to the y plus h of x. Oh, and did I forget something back here? Let me go back here. No, I forgot my plus c. Okay. So our solution, we're combining these two. We have some functions of y here that are not in this. We have a function of x here that's not in here. So our solution, f of x, y, is all that stuff. E to the x plus xy plus y e to the y minus e to the y plus 2y plus c equals 0. And we know that y equals 1 when x equals 0. So I'm going to plug that in. E to the 0 plus 0 times 1 plus 1 e to the 1 minus e to the 1 plus 2 plus c equals 0. I had to write all that stuff down so I didn't make an arithmetic error. So this is e to the 0 is 1. That's 0. This is e minus e. Those go away. And we get 2. So we get 3 plus c equals 0. So c is negative 3. To satisfy the initial condition. I'm not going to rewrite all that with c equals negative 3. We'll just leave it with c. We know what it is. Let's look at that one. Do we have time? Yeah, we have time.
This is fun when you don't have to draw it out. You can just see it.
Yes, it is. It does make it more fun. So what do we have? E to the x. Whoops, what did I do there? E to the x plus xy plus y e to the y minus e to the y. I like the asymptotic behavior there. E to the y plus 2y. And I'm going to put the minus 3 down here.
That's so sad.
Right. So we get a specific solution curve here for our initial condition. So yeah, I'm guessing they must loop around eventually. But this one's more fun to look at. C.
I agree.
Yeah.
What is it's a parachute.
Yeah.
It could be a very large parachute. Yeah, I see that.
It's a starfish that got thrown into a black hole.
All right, so for the homework, we're just going to do the first part, our homework. This is section 2.4, page 71, number 1 through 13, every other odd, and 25. And then we'll talk about integrating factors. When our equation is not exact, there are a couple of situations where we can find an integrating factor that will transform it into an exact equation.